Out came 7,000 metal balls. And then they brought out a heavy-looking wooden box. On its lid was a label that read "Danger." What's inside? Here it is, the world's strongest magnet, a neodymium magnet. They began to slowly lower the magnet. The metal balls started to twitch, but the magnet is still 30 centimeters away.
Wow! That's so cool!
The space between the magnet and the ground is packed with the metal balls. It's even more surprising to touch.
It's stuck! It won't budge. I can take a few off the surface, but the rest won't move.
Once the balls are stuck, they can't be removed by hand. They have to be pried off, like this. The neodymium magnet was invented by a Japanese researcher in 1983. Its strength took the world by surprise.
I just saw the demonstration, but could you explain why it's so powerful?
I'll use this to explain.
Okay.
This is an iron rod, and here are some iron balls. On its own, the rod doesn't have the power to attract the balls. But if you attach a magnet to the iron, like this, then the iron rod becomes magnetic. Detaching the magnet returns the rod to its original state.
Iron's atoms are actually small magnets, but because they don't point in the same direction, they cancel each other out, and the piece as a whole does not possess magnetic force. When a magnet is attached to the iron, all the mini-magnets turn to face the same direction. This causes the iron to become one big magnet. But once the magnet is removed, the mini-magnets in the iron return to their original direction, and the iron loses its magnetic force. This is where a metallic element called neodymium comes into play. Something amazing happens when neodymium is added to iron. Neodymium has the ability to keep the mini-magnets faced in the same direction. So even if the magnet is removed, the iron maintains a strong magnetic force. Thanks to neodymium, which allows iron to retain its magnetic force, the world's strongest magnet was born. Neodymium magnets contributed greatly to the development of energy-efficient air conditioners. When the Japanese government put strict energy-saving standards into place, which applied to any shipments from 2003, air conditioner manufacturers rushed to make modifications. After extensive research on ways to save considerable energy, they eventually focused on the motor. The exterior of both motors feature electric wire coils. But the inner rotating part of the new motor is very different. The electric wire coils have been replaced by neodymium magnets. These powerful magnets are used to rotate it. With conventional motors, electricity was sent to both the inner and outer part, and rotation occurred due to the repelling force of the two electromagnets. The new motor uses powerful neodymium magnets on the inside, so only the outer coils require electricity. Let's compare how much electricity each motor uses when rotated at the same strength. The new motor requires about 150 watts. This is half the electricity that the conventional motor used to perform the same function. Since 2003, almost all manufacturers in Japan have begun using neodymium magnets. The magnets have contributed significantly to energy efficiency. A revolutionary energy efficiency technology is being developed with neodymium magnets. This is Naoki Hirano, a researcher at an electronics company. He's working on a new type of cooling system. It's a magnetic refrigerating device. Let's find out how it works.
Here's a powerful magnet, a neodymium magnet. Now we'll put it...
A special metal is attached to the tip of the thermometer. When the metal is placed near the magnet, the temperature rises. And when it's pulled away from the magnet, the temperature drops 2 degrees. The metal's temperature is affected by changes in magnetic force. So Hirano had the idea of using this metal, which shifts temperature drastically, and the powerful magnet to create an efficient cooling system. First, a narrow container is filled with this metal. The container is then placed on the inner side of the cylinder. In the center of the cylinder is a powerful neodymium magnet. When it rotates, the magnet alternately moves near, then away from the container. They then skillfully harness the cooling that occurs when the magnet draws away. The device is attached to a refrigerator. The device is then turned on. At the starting point, the inside of the refrigerator is 20 degrees, close to room temperature. Let's use a thermographic camera to see how the temperature changes. The inside of the refrigerator gradually changes from red to blue. The temperature is clearly dropping. About 15 minutes later, the refrigerator has cooled to about 4 degrees.
It's said to have the strength to double the efficiency of current air conditioners and refrigerators. With magnetic cooling, the stronger the magnet is, the higher the efficiency and power. So the strength of the magnet will be very important.
Dr. Mizushima, I'm impressed at how neodymium magnets cut power consumption in half, and I didn't know that it could be used in cooling devices.
Researchers both in Japan and abroad are working on the development of magnetic refrigerating devices. So far, they've developed one that has cooling capacity that exceeds 1,000 watts, and the research is still ongoing.
I can imagine that the need for neodymium magnet motors will only increase.
Yes, however, neodymium magnets have their own drawback. One is that they are vulnerable to heat. Motors rotate at high speeds and generate a lot of heat. So, this weakens the magnet's magnetic force.
Is there a way to solve this problem?
Yes, the solution is to add a rare earth called dysprosium. Having 1% of dysprosium is said to increase the heat resistance by 15 degrees. But the problem is that dysprosium is a scarce rare earth, and the world's top producer, China, is limiting exports. To keep technological progress from coming to a halt, Japan needs to develop a technology that takes away the need for dysprosium.
Coming up, we have a study on a way to increase the heat resistance of neodymium magnets without using dysprosium. How far has research progressed? Let's find out.
This is Masato Sagawa, the inventor of the neodymium magnet. He is currently involved in a national project to reduce the need for dysprosium.
It's used in the manufacturing of motors in hybrid cars, which are very promising, and a variety of electric cars. If we don't find a solution, then production will come to a halt. So it's an issue for the government and Japan as a whole.
This is the new neodymium magnet that Sagawa and his team are developing. The key is in the size of the magnet's particles. This magnet's particles are roughly 3 micrometers. They're much finer than regular magnet particles, which are about 5 micrometers. The finer the particles, the greater heat resistance it has even without dysprosium. The mini-magnets within the neodymium magnet particles are all facing the same way and have strong magnetic force. However, if the heat disrupts a part of the particle, then the disruption gradually spreads throughout the whole particle, and the particle loses its magnetic force. But if the particles are small, then even if some are ruined, the damage to the magnet as a whole is relatively small. The disruption of the mini-magnets are contained within the particle and do not spread to other particles. Data shows that this method successfully increases the metal's heat resistance without requiring dysprosium. However, there's a major roadblock to this method. When comparing the particles of varying sizes side by side, the 3 micrometer particles automatically started burning. Because neodymium is highly reactive, the increased surface space comes into contact with the oxygen in the air, and it catches on fire. To handle the fine particles, the group is looking into a way to conduct the entire magnet production process in a non-oxygen environment. Plans are being made for the construction of a mass production facility.
The national project to reduce the need for dysprosium is still ongoing. According to Sagawa, they've been able to make neodymium magnets that can withstand 200 degrees Celsius heat with just 1/3 of the original dysprosium content. Of course, their goal is to completely eliminate the need for dysprosium. Well, it's good to know that they're making steady progress.
Yes. Besides developing technology to reduce dysprosium, researchers are looking for ways to reduce the amount of rare earths that is wasted during production and develop a recycling system. They are also working to find new rare earths. History has proven that necessity is the mother of invention, and it's led to many scientific breakthroughs. Perhaps this will be true for Japan's magnet research as well. I look forward to future progress.